In this section, we're going to be discussing antiderivatives and the rules of integration. What we've done in the past is we've taken derivatives, and the derivative was the slope of the tangent line. And when we took some derivatives, we could see here it's three functions. We've got x squared, we have x squared plus 7, and we have x squared minus 54. Now, if you take the derivative of any of these functions, you're going to get the same answer because the derivative of a constant is 0. So the derivative of x squared is 2x. The derivative of x squared plus 7 is also 2x. Antiderivatives are working backwards. So you start with a function such as 2x, and you ask yourself the question, well, what function has derivative 2x? And just for this one example, I have 3 functions at least that will satisfy that. And in fact, there are an infinite number of functions that will satisfy that. But the answer to that question, what function has derivative 2x, is what we call the antiderivative. It's working backwards. More often we call that an integral. Now, here, when you work backwards, since you have a function, in this case 2x, the integral is going to be x squared. But that could be x squared plus or minus almost any number you can think of. So, because we want the most generic answer possible, we say that the integral, or the antiderivative, is x squared plus c. And you really must have that plus c in every antiderivative. Otherwise, you've missed many of the choices. Now, we don't want to have to keep asking the question, what function has derivative 2x, or what function has derivative x squared plus 3x plus 7? So we invented this symbol, and that symbol is this funny looking s. It's the integral symbol, and that symbol essentially means what function has the derivative, and then whatever you put in there is the derivative. So in the case of the 2x equation, you would write here, the integral of 2x is equal to x squared plus c. Now, all of these integrals have a dx on them, and that shows up because of the chain rule. Now, we're going to talk about that in a little more detail in the next section, but I will very briefly show why that dx might show up, why the dx does show up in these calculations. So here, if we start off with an equation y prime, or f prime, equals dy dx, this is the derivative. That's the derivative right there. And if you want to work backwards, what I'm going to do is I'm going to take this f prime equals dy dx, and I'm going to move all my x terms to one side of the equation and all my y terms to the other side of the equation. In this particular case, dy is the only y term. This is my y term. And the dx gets moved over with the f prime. And now, if you can think of this dy as the derivative of y. In some sense, that's what the d stands for. So dy dx stands for the derivative of y with respect to x. And so if you integrate dy, Well, if you do the antiderivative of the derivative of y, you get back to y, and that's down here on the very last line. So the integral of dy is y, and the integral of f prime of x dx is f of x. And of course, don't forget your plus c. So dx for us right now shows up because our derivative was dy dx. And the integral of the dy became y, and the dx was associated with the x part of the equation. Here are some basic formulas, and you're going to want to memorize these. The simplest one is the integral of a constant. Here k is a constant. K is a constant. And so the integral of k is kx. And you can check any of your integrals by simply taking the derivative on the right-hand side. So here, if we start off with kx, suppose we had f of x equals, well, in this case, we'll just do 7. Then f prime of x, so if f of x is 7x, then f prime of x is just 7. So if you integrate 7, which is a constant, you get 7x. So if you start at the top and work down, that's a derivative. If you start at the bottom and work your way up, that's an integral. So it's just a question of which direction you're doing the operation. We had a basic power rule for derivatives, and the power rule for derivatives, so we have the derivative of x to the n. Our rule was 1. Multiply by the exponent, and then subtract 1 from the exponent. If you want to work backwards to do an integral, you have to truly undo everything you did. So for an integral, we want to work our way back up this list. So for the derivative, we did multiply first, then subtract. For the integral, we're going to add first, and then we're going to divide. So in the derivative, it was multiply by the exponent, subtract 1 from the exponent. For the integral, it's going to be add 1 to the exponent, divide by the exponent. And that's what this rule number 2 says. It says if you have x to the n, you add 1 to the exponent, x to the n plus 1, and you divide by that, divide by n plus 1. And don't forget your plus c. Rule number 3 says that if you have a constant times a function, you can take the constant out in front of the integral. You can always move a constant out in front of an integral or back inside the integral if you need to. Integration, you can distribute over addition and subtraction. So the integral of f plus or minus g is the integral of f plus or minus the integral of g. That does not work with multiplication. If you have two functions multiplied together, you need a different rule. Number 5 is probably the easiest rule. Since the derivative of e to the x is e to the x, then the integral of e to the x is also e to the x. And number 6 is the one that is the easiest to forget. And here we have the integral of 1 over x, and the answer there is the natural log of x. And the reason is because the derivative of the natural log of x is 1 over x. Now you'll notice that here we have an absolute value. And the reason we have the absolute value is because we're not allowed to put negative numbers into a natural log. You cannot take the log of a negative number. So on the left side of the equation, in the 1 over x part, we're allowed to put in negative numbers. And so we'd like to be able to put those same negative numbers into the right side of the equation. So we put an absolute value on that. Then, no matter what we put in there, it's always going to be positive. And I'm going to make a note of that. Can't take a log of a negative number. So, here we have a few examples. It says to integrate the following. So, for the first one there, what we're going to do is we're going to simply apply the rule. And the power rule for integrals says, if you're going to work backwards, you add 1 to the exponent, so that's 3 plus 1, and then you divide by that, 3 plus 1. And don't forget to add c. Now generally, we only do the 3 plus 1 the very first time, because after that, we can generally recognize that 3 plus 1 is 4, and so here we would just write x to the 4th over 4 plus c. And that's really all there is to it for a simple polynomial like that one. For number 2, it's a little more complicated because I have 1 divided by x to the 4th. Now here, I don't have a rule for x to the 4th in the denominator, so I want to move it to the numerator. So the very first thing I do is I rewrite this as x to the negative 4. Now I can apply the rule. And the rule says, add 1 to the exponent. And whenever you add 1 to a negative number, just make sure you do that correctly. Minus 4 plus 1 is a negative 3. Divide by that negative 3. And don't forget to add c. So you have to make the problem look like one of those 6 rules that we have. Here's another one. We have 1 divided by x squared. And I'm going to do the same thing. I'm going to rewrite this. It's going to be x to the negative 2. The dx is still there. Same story. Add 1 to the exponent. Minus 2 plus 1 is minus 1. And then you divide by the exponent, negative 1. And don't forget to add c. A lot of times if we're dividing by negative 1, we don't generally write that. So very often you'll see this answer written as negative x to the minus 1 plus c. Now, number 4 looks very similar to 2 and 3. And so I'm going to create a new page here. And I want to talk about this one for a moment. If you try to solve this problem the same way we did the other two, what you would try to do there is you would try to write x to the minus 1 dx. That's just rewriting it, moving it to the numerator. And then you would say, oh, well, let me see, I'm going to add 1 to the exponent, and I'm going to divide by that. But the problem is that when you do that, here you're trying to divide by 0. And you can't do that. So when you run into a situation like this, where you've used the usual rule and you end up dividing by 0, you have to stop and think, I must be doing something wrong. And this is not the way to do this problem, of course. What you want to do is you want to remember the rule, number 6. The integral of 1 over x is the natural log of x. This is going to be the natural log of the absolute value of x plus c. And the big reason that rule is so hard to remember is because anytime you have a polynomial and you take the integral or the derivative, you end up with a polynomial. If you start off with an e to the x and you take a derivative or an integral, you end up with an e to the x. But here, you start off with something like 1 over x and you end up with a natural log. So the stuff on the right doesn't look anything like your answer on the left. It's still correct, of course. Sometimes we have fractional exponents, and those are no more difficult than the integer exponents, except you have to be careful when you do the subtraction, the addition, of course. A lot of times I'll do the addition on the side here. Minus 5/4 plus 1, because I'm going to add 1 to the exponent. That would be minus 5/4 plus 4/4, which is negative 1/4. So here, when I integrate, I add 1 to the exponent, I get negative 1/4. You divide by that, and you add c. Here again, a lot of times you'll see this simplified. If you have a fraction in the denominator, you can flip it over and bring it to the numerator. So you might get something that looks like negative 4 x to the negative 1/4 plus c. Also the correct answer, and then involves fewer fractions. For number 6 here, we have addition. We have x squared plus x to the minus 3. What you can do here when you have addition and subtraction is you can just integrate each term individually. So I'm going to integrate the x squared, and I get x cubed over 3. I'm going to integrate x, and I get x squared over 2. And I'm going to integrate x to the minus 3, and I get x to the minus 2 divided by negative 2, and you just put one single plus c on the entire expression. You don't need to put a plus c for each of the 3 separate integrals. For number 7 here, what I'm going to do is I'm going to rewrite it just a little bit. I am going to distribute the integral, but I'm going to take and I'm going to write this x divided by 2 is 1/2 times x. So here we have the integral of 3 dx plus the integral of 1/2 x dx plus the integral of e to the x. And the reason I'm doing that is to show you that I can factor out that 1/2. We have the integral of 3 dx plus 1/2 times the integral of x dx plus the integral of e to the x. Sorry, forgot my dx. So the integral of 3 is 3x. The integral of x is x squared over 2 times that 1/2. And the integral of e to the x is e to the x, and you just stick one single plus c on the end of that. And that's your basic integration. Basic polynomials, natural logs, and e to the x. Now, each one of these problems had this plus c on it. And sometimes you can actually solve for that plus c if you happen to know something about the problem. That's a little typo. So if you know something about the equation, you can solve for c. And this piece of information is called an initial value. So for example, in this case, I have a derivative. F prime of x is 3x squared plus 4x minus 1. And I have my initial value. I know that in the original function, when I plug in a 2, the answer is 9. So when I'm done integrating f prime to get f, I can find my constant, because I know that when I plug in 2, it all has to add up to be 9. So that would look something like this. So f of x is going to be the integral of f prime of x dx, which is going to be the integral of 3x squared plus 4x minus 1 dx. And if you integrate that, you get 3x cubed over 3, and those 3's are going to cancel. You get 4x squared over 2, and you can divide 4 by 2. And the integral of 1 is just x, and plus c. So now to solve for c, I'm going to use that initial value. I know that f of 2, so if I plug in a 2 here, I'm going to cancel the 3's. I get 2 cubed, and then 2 times 2 squared, and then minus 2, plus c. And that all has to add up to 9. And so that's 8 plus 8 minus 2 plus c equals 9. And c must be equal to negative 5. So you can take that c, and you can put it back up here in that f of x. I need a new page to write that. So my answer is x cubed plus 2x squared minus x minus 5. Let's make sure that's right. X cubed plus 2x squared minus x minus 5. I was able to solve for my constant, and now if you need to do something with this equation, you can, because you don't have an unknown value of c. So sometimes this comes up in the context of word problems, and you may recall from before that we had something known as the marginal cost, and the marginal cost is the cost to produce the next item. You can also talk about marginal profit or marginal revenue, or you can put marginal in front of almost anything. So the marginal cost is also the derivative. So if c of x is the cost function, then c prime, the derivative, is the marginal cost. So if you happen to know the marginal cost, the cost to produce the next item, you can simply integrate that to find the cost function. And that's what we have down here. So if you know the cost, you can take the derivative to find the marginal cost. If you know the marginal cost, you can use the integral to find the cost. So here in this example, it says that the Lorimar Watch Company manufactures travel clocks. The daily marginal cost function associated with producing these clocks is given right there. And C prime, the marginal cost, is measured in dollars per unit. X denotes the number of units produced. Management has determined that the daily fixed cost incurred in producing these clocks is $120. Find the total cost incurred by Lorimar in producing the first 500 travel clocks per day. So whenever you get to a word problem, it's nice to know what all the numbers mean. Well, we know that C prime, that's the marginal cost function. So if I want the cost, so it says find the total cost. The total cost is going to be the integral of the marginal cost. Now the problem is that when I calculate that value, I'm going to get some formula plus C. And I'd like to know what that plus C is if I want to actually estimate my costs correctly. So that's where this other $120 comes into play. It says the daily fixed cost is $120. That means if Lorimar doesn't produce any travel clocks at all, it still costs them $120. So that says that the cost of producing no clocks is $120. And that's my initial condition. C of 0, the cost of producing 0 clocks, is equal to 120. So when I integrate this, so I'm going to get the integral of 0.0000009 x squared minus 0.009x plus 8. So if you integrate that, you get 0.00009 x cubed divided by 3. Even though I have that very small decimal in front there, you just add 1 to the exponent and divide. And then minus 0.009 x squared divided by 2. The integral of 8 is 8x. So don't forget to put your plus c on the end of that equation. So I'm going to rewrite that cost function at the top of the next page here. And I'm going to simplify it a little bit. 0.0000003 x cubed minus 0.009 x squared over 2 plus 8x plus c. And what I know is that the cost of producing no clocks, which means if I put in a 0 here for x, I get c is 120, which means my cost function is 0.00003 x cubed minus 0.009 x squared over 2 plus 8x plus 120. And the original question wanted to know what was the cost of producing the first 500 clocks. So you put 500 into that equation. Okay, 500 cubed minus 0.009 over 2, 500 squared, plus 8 times 500 plus 120. And if you plug that into your calculator, you get $3,370. That is the cost to produce the first 500 clocks. Now, as I mentioned, you can have marginal cost, but you can also have marginal profit. And so here we have another word problem. We have Canon Precision Instruments, and they're making an electronic flash, and the marginal profit associated with producing and selling these electronic flashes is given by this equation. P prime is negative 0.004x plus 20. Now it says when the production level, that's when the production level is x units per month. It says Canon's fixed cost for producing and selling these electronic flashes is $16,000 per month. At what level of production does Canon realize a maximum profit? What is the maximum monthly profit? So here we have a more complicated situation because we want to know both the maximum profit, but we first have to find out at what number of flashes produced do we get that maximum profit. And you may recall that to find your maximum profit, you take the derivative of the profit function, p prime of x, and you set it equal to 0. That was from our previous chapter on maximums and minimums and optimization. So if you want to find maximums and minimums, you take the derivative, which we already have, and you set it equal to 0. The other thing is that the profit is going to be given by the integral of the profit function, of the marginal profit function, the integral of p prime of x, and we have an initial condition. It says that the fixed cost is $16,000 per month. And so that means if you produce no flashes, your cost is $16,000. And since that p function is a profit function, that means that any cost I have comes out of my profit. So I have to put that as a negative. I'm going to make a note of that. Negative because it's a cost. And anytime you have a cost, that comes out of your profit. So that's what we have to do. So at what level of production does K9 realize a maximum profit? That's when the derivative is 0. Then you integrate the profit, the derivative of the profit function there, your marginal profit, to find P. So let's do that. So max profit P prime, which was negative 0.004x plus 20. That has to be 0. And if you solve that, you get that x is equal to 5,000. So they have to produce 5,000 flashes for maximum profit. Then you want to find out what is the maximum profit. So you need P of 5,000. To do that, you need a profit equation. And so P of x is the integral of P prime of x, which is the integral of negative 0.004x plus 20 dx. And if you integrate that, you get 0.004x squared, add 1 to the exponent, and then divide by 2. And the integral of 20 is 20x. And don't forget your plus c. And now you can solve for c, because P of 0, if you plug in a 0 there, you get c. And we know that that's negative 16,000. And so you take this 16,000 and you put it in here for plus c. Now, so I don't have to rewrite this equation, I'm going to cross off the plus c, and I'm going to put a minus 16,000. And now we can find the maximum profit. So P of 5,000 is negative 0.002 times 5,000 squared plus 20 times 5,000 minus 16,000, and it turns out that that maximum profit is $34,000. So when you're doing these word problems and they're asking for a maximum or a minimum, you still have to remember all the things you did with derivatives. And anytime you want to find a maximum or a minimum, you have to take a derivative and set it equal to 0. For many of these problems, you will be given the derivative. That concludes the lesson on basic integrals and antiderivatives.